Hello, Scotty. So this is a video about integrals and how they work and all that good stuff. So, okay, you're familiar with the idea that if you have a function f of x and then you take the derivative, then you'll end up over here with f prime of x. Well, so if you want to get back to the original function, that is exactly what an integral does. So an integral, also called an antiderivative a lot of the time, takes you from f prime of x, you take the antiderivative, and that brings you over here to f of x. So if you have some function f and you want to know what its derivative is, you do the derivative, which you're already well versed in. And then if you have the derivative and you want to know what the original function is, then you take the antiderivative, and that brings you back over here. So just as a quick example, if you take, let's say that you have the function x to the fourth plus x squared, right? If we take that over here, we know that the derivative of that is going to be 4x cubed plus 2x, right? Just using simple derivative. And so then if we take the antiderivative of that, if you take 4x cubed, you're going to get x to the fourth. If you take plus 2x, you're going to get x squared. So you do an antiderivative exactly the opposite of the way that you would do a derivative. So if you're trying to solve for it, you do the opposite of the power rule. So you just bring the 4 to the top, you increase the exponent by 1, right? So this x to the third will become x to the fourth. And then, so you see what would have been here beforehand, and you see that there's no coefficient out in front of the x to the fourth. So, for example, if instead of that, if you started with, let's just make this simple. Let's say that you started with x cubed plus, let's say 3x. Okay, so if you know the derivative of some function is x cubed plus 3x, then what would its antiderivative be? What would be the original function that gives you this derivative? So what you do is you take this back over here and you solve for the antiderivative. So you say, okay, the exponent goes up by 1, so you're going to have an x to the fourth right here, and then you're going to have plus 3x, so that exponent's going to go up by 1, so you're going to end up with plus 3x squared, except that one little piece that you're missing. Okay, so this x cubed, that goes up by 1, right? So now you have x to the fourth over here, except that what happens when you take the derivative of this? You end up with 4x cubed, and over here we just have x cubed. So then what you do is you just do 1/4. Okay? So if we took the derivative of this, we would have 1/4 x to the fourth, and you take the derivative and you get 4 over 4 x cubed. Right? So take the derivative of this, you get 4 over 4, which just is 1. So you have a 1 right out here. And then that's where you get the x cubed from, x cubed. So then with this 3x, you need to do the same thing. So if you took the derivative of this, you would get 6x. So what we do is we put a little 2 there. So, yeah. So if you start with the antiderivative, you increase the exponent by 1, and then you make the coefficient out in front 1 over the new exponent, or in this case 3 over the new exponent. So x to the third, the antiderivative of that is 1/4 x to the fourth. This 3x, the antiderivative of that is 3x squared divided by 2, or 3/2 x squared. Okay, so pretty simple. And then another thing that people will do if you're starting over here and then you go and take the antiderivative, another thing they'll do is they'll do plus c, and we'll get to that later. But the main thing is, so if you have some function of x and you take the derivative, you get f prime of x. If you have f prime of x and you take the antiderivative, you get back to f of x. So that's kind of the big picture of how derivatives and antiderivatives all work, right? So you've got f of x, derivative, f prime, antiderivative, f of x, also called the integral. Just one quick thing for notation's sake, so that you don't get confused if you see this later. A lot of times people will, so right here we're taking, let me scoot this up. Right here what we did is we take f prime of x and we take the integral of f prime, right? And so then we're calling that f of x. But really, if you have the integral of f prime of x, you can call this function whatever you want. So you can call this f of x. You could call this g of x if you want to. And so the thing that some people will do is, if they start with the integral of f of x, dx to be specific, so if people start with f of x, if you start with a prime, then it's very conventional to just go to f of x, right? F prime goes to f. That makes sense, because then you go from f to f prime when you take the derivative. If you start with f, and so you don't have a prime in here, it is often conventional to just name this as capital F of x. That is a very common thing you'll see people do. So that's all they're doing, is you can name this whatever you want. It's just very common to name it capital F of x if you don't have the prime here. So here, the integral, or the antiderivative of f prime is f. Here, the antiderivative of f is f prime. But this is all just labels and conventions and names, and you can call it whatever you want. The main thing you want to remember is this. If you start with a function and you take the derivative, the opposite of that is the antiderivative, and it gets you the original function back. Or if you start with some function over here and someone asks you what is the antiderivative, then this is the process that you go through. You do a series of things that will let you figure out what was this original function. Now, the one place where, let me show you where this doesn't always add up, and essentially why we need this plus c right here. Let's say that we have the function x squared plus 7, right? And then let's say we also have the function x squared plus 1, right? So what happens if we take the derivative of x squared plus 1? Well, we're going to get 2x from the x squared, and then the derivative of 1 is 0, so you're just going to get 2x, and that's the whole thing. Well, so then if we take the antiderivative of this, you'll notice we come back here, and we're just going to get the x squared portion. So if you take the antiderivative of 2x, if you say what function gives me the derivative 2x, the only function that gives you the derivative 2x is x squared. But so then where did this plus 1 go? And the same thing, if you take the derivative of this, x squared plus 7, you're going to get the same thing. You're going to get 2x as the derivative of x squared plus 7. So then when you take the antiderivative, if you're saying what function gives me this derivative, because that's essentially what an integral is, or what an antiderivative is. You're saying what function over here will give me this derivative. And you'll notice that x squared plus 7 gives you 2x, but x squared plus 1 also gives you the derivative of 2x. And so that's why when we take the antiderivative, so if you start with the function 2x and someone asks you what is the antiderivative of 2x, then when you come over here you need to put x squared plus c, some constant c. You know that there isn't going to be any x term in here, because if there were an x, it would show up in the derivative, because only the derivative of a constant is 0 and goes away. So the derivative of a constant goes away, so that's why when you take the antiderivative, you need to add it back. You need to add back in some unknown constant, and we don't know what this c is. It could be 1, could be 7, could be anything. So that's why people add in this plus c at the end when you take the antiderivative of a function. Okay, so that is kind of the overarching idea. That's the relationship between functions and their derivatives. They're connected by derivatives and by antiderivatives. Okay, so the second thing, okay, so here we have a graph. So I'm going to use the same idea, the x squared idea. Okay, so let's say that we want to graph x squared, right? So that is 1, 2, and 4, right about there. And something like that. Okay? So that's somewhere around x squared-ish. And then let's say that we wanted to graph x squared plus 1. Well, that's just right here, right? You just move everything, all your points just move up by 1. Right? So this is x squared plus 1. And then somewhere up here, it won't be quite right, but 1, 2, 3, 4, 5, 6. So this is 7. So this is x squared plus 7 up here, right? So again, going back to the relationship between derivatives and antiderivatives, when we take the derivative, what you're asking is, what is the slope of the function at any given point x, right? So the derivative of a function is the slope of that function. So if you take the okay, going back to this. So if you take this function, x squared plus 7, or x squared plus 1, or x squared plus c, when we take the derivative, we're asking what is the slope at some point x. And the slope is 2x, right, for all of those things. So right here, the slope is 0, right, because 2x, if x equals 0, is 0. If x equals 1, the slope is 2x, so the slope is 2, right there. When x is 2, the slope is 4, right? So the slope, the tangent line that touches right here, is going to be 4. Here it's going to be 6, right? But you'll notice that this graph up here, this x squared plus 1, has the exact same slope at all the different points. So if you have, here you have the slope is 0, here the slope is also 0, and here the slope is also 0. And so that's why when we're looking at this relationship here, all three of these equations, all three of these functions are going to have the same slope, right? All three of these are going to have the slope 2x at any given x. And so that's also why if you ask the question backwards, if you say what function has a slope of 2x, if you ask that right here, what function has a slope of 2x, well, you can see that all of these have a slope of 2x. They're just separated by different constants. So that is how you get the idea of functions, their derivatives. This is the slope of that function. So if you're asking what function gives me this slope, then you're going to have what we call a family of functions, or a family of antiderivatives, or however they want to say it. Because all of these, and obviously you can put in any constant here, all of these are going to be an answer to this question: what is the antiderivative of f prime of x? Okay, so next we will talk about how you get area under a curve.